Hello everyone, and welcome to today's 1W-Minds talk. Today's speaker is Nadav Dym, a senior lecturer at Technion University. He obtained his PhD from the Weizmann Institute in 2018 and was a postdoctoral researcher at Duke before joining Technion. His research is in broad terms about mathematics about machine learning and spans both optimization, approximation theory, and geometry. Today's talk is not an exception. Its title is Efficient Invariant Embeddings for Universal Group Invariant Neural Networks. The floor is yours.
Yeah, thanks. I see I changed the title, but that's okay. Yeah, so anyway, let me start. Okay, so I'll start with explaining the words universal group invariant neural networks from the title for a few slides, and then we'll continue. So start with universal neural network. So there's this famous universality theorem, perhaps I think maybe the most known theoretical result about machine learning, or one of, which says that fully connected neural networks can approximate continuous functions to arbitrary accuracy, and that's it's from the 90s basically. Various versions of it appeared in various papers. So that's a pretty well-known result. And what we're going to talk about is coupling this with group invariant neural networks. So the setting there is we have, say we have some learning problem where we want to learn some function f using a hypothesis class capital H. And we know that the learning task we have as some sort of symmetry. So for example, in this picture, you see that, f is the function that takes images to their semantic meaning, takes an image of a cat to the word cat. And that is a translation invariant function. And you would like, it would seem sensible to incorporate this into your model or hypothesis class and make a function class H, which incorporates that. Indeed, convolutional neural networks up to some details can be seen as translation invariant models, which respect that, and they work for images very well. So that sort of seems to have been the motivation to talk about this in other domains. There are many other examples. So I think the most popular examples are, one is graphs. So we will have, right? So you learn, there's this task of learning on graphs. Graphs can represent a lot of different objects in nature. And there you have some sort of permutation symmetry where if you have the same graph, but the nodes are labeled differently, it would be represented differently in the computer, and you have to take that into account. So yeah, so what people typically call graph neural networks typically are invariant to this type of relabeling. And what I'm going to talk about today mostly, we will talk about graphs at the end if we have time, but mostly going to talk about point sets. So, okay, so here's an example of a point set, which happens in sort of computer vision type applications. You have a bunch of points in 3D, which represent this chair in this case, or some 3D object. And basically, it's some matrix, n by 3 matrix, or sometimes we denote it like this as a set, because really, there's no sort of natural ordering in the points, and you want to be invariant to the ordering. So yeah, a different way of saying this, if you do think of it as a matrix, is that this should, this function should be permutation invariant. So changing the order of the points shouldn't matter. I didn't say that it would begin. If you have questions along the way, I don't know what the rules are, but for me, it's fine. I'd be happy. So, okay, right. So SN is our notation for permutations. Okay, another example. So basically, we're going to be focusing on these two examples on point clouds and its symmetries. So one are permutations, another is rotations. So here you have, right? So if you have different rotations of an object, often that doesn't matter to your task. So say you have a rotated chair, it's still a chair. So here your symmetry group is SOD. So it's functions that are orthogonal, and also their determinant is 1. So we don't allow reflections. Okay. Okay. Right. So you have these symmetries, and you want to build some architecture or model that respects that. For example, in the permutation invariant case, so you have these n points, which are denoted as a set. We don't care about the order. One natural way and very simple way to build a model that respects that is to do what you see here. So you take basically this is built out of two fully connected neural networks, N1 and N2. You apply N1 to each point separately. And that sort of gives you, per each point, you get a different feature. Then you sum that all together, and then you apply some other neural network N2 from outside, sorry. So you can see that this is sort of, because sum is permutation invariant, this is permutation invariant. And so that's like one sort of standard example. It's, I see, somehow I erased the references. So this is sort of called the deep sets or point net in the literature. Somehow the references disappeared, I'm sorry. Okay, another, okay, and then you also have a lot of point net networks for rotations and permutations together. I'm not gonna talk about how they look exactly because they're a little bit more complicated, but there is such a thing. And basically what, yeah, sorry. Okay, so anyway, so there are these group invariant neural networks, and then this concept of universal group invariant neural networks is basically to discuss universality for these different models which people are suggesting, or suggesting new models which have this universality property, right? Be it images or point clouds or graphs. So so the idea is that if previously we know that the regular universality result says that continuous functions can be approximated by fully connected neural networks. So you'd like to say that your model for continuous invariant functions can be approximated by an invariant architecture, right? So invariant architecture by construction is some subset of the set of continuous invariant functions. Can only approximate invariant functions, but you'd like to be able to do everything. Okay. Right. So for example, you'd like to say that if we look at this model we discussed before for permutation invariance, where you apply the neural network, first neural network, you sum, you apply the second neural network. So you'd like to say that this thing is universal. So can approximate any permutation invariant function, which I think is actually not so intuitive, but turns out to be correct. So it seems like, I don't know, I think that the intuition would be that you're leaving a lot of money on the table here if you just do the same thing at all points and use sum, but it turns out that you can approximate all permutation invariant functions in this way. So this was suggested and also proven in this deep sets paper originally, but we'll still be talking about some of the finer details there later on. Okay, so throughout this talk, we'll have some mathematical assumptions, which we're going to state once and then forget about. So they're all going to be encoded in this word nice. So you have capital G, a group, and V, a real finite dimensional vector space. G is a compact matrix group defined by polynomial equations. And the map that takes G comma V to GV, basically the group action is a polynomial map. Okay, so that's, in particular, these assumptions are satisfied for SOD and SN, and most of the examples that people are interested in, maybe the compactness. There are some examples which doesn't hold, but compactness is very helpful, so we assume it. Okay, so we're making these assumptions. We're going to state some results based on these assumptions. Basically, usually these assumptions can be weakened for these various results, but it's convenient just to work like this. Okay, so the first thing I'm going to do now is basically replace the idea of universality with the idea of separating invariants. So let's define that first of all. So you have a group acting G acting on V, and you have a bunch of functions, these orange H's, and these are called well, they're invariant if they're invariant, just group invariant, and then they're separating if, in addition, you sort of have the other direction. So if hi of u equals hi of v, so if hi of u equals hi of v, for all I, that means then u equals v. Okay, so essentially you can think of this as in terms of the quotient map, quotient space, you can understand why this means. So you have this quotient space of, orbits of V under the group. And then invariance basically means that the map that you can define, you can identify this mapping H1 to HM with a well-defined mapping on the quotient space, right? Because you can define this and it doesn't depend on the representative because of the invariance. And then the separation is basically injectivity on V on the quotient space. So that's good. Okay, one sec. I'm going in the wrong direction for some reason. Okay, and then you can sort of rather easily prove a theorem that says that if you have a bunch of separating invariants, then you can approximate any continuous invariant function by a composition of, you first apply these functions, and then you apply some continuous function from outside, which you could also replace it with a fully connected neural network because of their denseness. But this function has no symmetry constraints or invariance constraints on it. So that the general idea is that this sort of gives you some sort of model class, which is universal. Okay, so okay, so let's, one second, maybe I'll go back to here. So again, the idea is basically now that we can just focus on separators. Okay, so we really, if we have separation, we have universality. So let's talk about, okay, an example of separation just to get some intuition. Okay, so here we have one of our two groups we're talking about, the special orthogonal group in 2 dimensions, acting on basically 2 by 2 point clouds, 2 points in R2. And then we can try to think of invariants for this action, right? So when so one natural option, or two, I guess, is taking the norm of the first point and taking the norm of the second point. Both of these functions are invariant to rotations. So that is invariant, it is not separating. So what does that mean? So you can see that if you take these 2 blue points or these 2 red points, they, in terms of these 2 invariants, they get the same values, right? Because they're all in the same circle. But in terms of, but they're not equivalent in terms of the group action, because you can't rotate these 2 points to these 2 points because the angle is different, the distance is different, right? So what you need to do is add a distance, and that sort of excludes this example, right? So at least now these 3 invariants will be able to separate the blue from red. That still leaves us with a problem that comes from the fact that we do not allow reflections. So basically, if I reflect the blue point x1, take it to the other side, so that in terms of norms and distances, that gives me the same pair of points, but in terms of, but it's not related by a symmetry because we don't allow reflections. So you can deal with that by adding some sort of orientation term. So like the determinant of the 2 by 2 matrix is defined by x1 and x2. And after you did that, so these functions h1 to h4 are separating invariants, which means that, for example, if you want to now construct a family of functions invariant to SO2 on this space, you could just take some neural network and apply it to these 4 functions, and that would approximate all functions. So that's good news. Okay, and this, in a way, this is also a sort of special case of a general philosophy, which I think was used a lot in the sort of literature about universality and invariant networks. And one nice example is Yarotsky's paper, where he sort of talks about things very nicely and formally and generally. So he talks about this theorem by Hilbert, which says that any so there exists a finite number of invariant polynomials, for some v acting in g, which basically generates all invariant polynomials. So any invariant polynomial can be written as some polynomial applied to f1 to fn, some sort of algebraic combination of these polynomials. Okay, so yeah, sort of in the algebraic language, that means that these functions are generators the ring of invariant polynomials, whatever. Right, you can see that in our conditions, generators will always be separators because, so basically, if you can show that any continuous function can separate points, which you can, then you can show that any polynomial can separate points, which you can, and then because of this property, you can see that basically F1 to Fn must separate points. So that's a good tool. So we basically have these generators all the time. We can always use them in theory. But some possible challenges could be that, so one thing could be whether we can explicitly compute the generators. So the theorem just says they exist. So often you can. In invariant theory, they have a sort of strange term. They call it the first fundamental theorem for SOD, OD, SN. And sort of a classical invariant theory results, which people have used. We'll see examples soon. Another question you could ask is how big n is, or sort of maybe expected to depend on the dimension of the space you're working in, but how large can it be? That's going to sort of be a main point that we're going to talk about, that often this can be very bad. And we're going to try to fix that. And again, we'll go back to our permutation and rotation examples, and we'll see that. And the last question, which you could also ask, is whether this model we discussed of basically applying polynomial invariance and then applying a neural network from outside, whether that is really what we want to do. It's not really what people do in practice. So ideally, you'd like to maybe do something else. Or have analysis that can take that into account. So we'll also deal with that in a way. Okay, so these are our challenges. Okay, but so let's see how this works, for example. So let's start with the permutation case. So right, we have x1, xn, those are points. You have the permutations, the action of permutations, and then when d equals 1, the generators are the constant function and this power sum polynomials. So you can take all these points and sum, take the sum of the points squared up to the power of n. So these are all invariant polynomials, and it turns out that these are generators. And in 1D, this is, in terms of cardinality, this is actually the best you can do. So, right, you could ask, maybe I can separate better with some, some other functions, maybe of some other sort or something, but turns out that really there is some sort of bound here that you can't separate using any type of sort of applying function and then summing. You can't separate with less than n functions. So that's actually not so difficult to prove, I think. And sort of a dimension argument could do it. Okay, so there we don't have an issue in 1 dimensions. And the sort of the context, so this is a question that there was quite a lot of sort of work on in the machine learning world. So this sort of came after sort of rather famous papers about learning on sets and learning on graphs, which talked about that you can actually take a single function like this, and that would be sort of separating or injective as long as these xi's live in some discrete world. So let's say integers or maybe even rational numbers, especially if you don't take continuity into account. And then there was some sort of conjecture that maybe you can actually do this with one function even in higher dimensions. So that's, as long as you require continuity, that's not true. Okay. Anyway, so but the bottom line for us is that generators in 1 dimensions are good. They have good cardinality, but this changes in the multiple dimensions. So if now your points xi are d and d is larger than 1, then you can have n plus d choose d generators. They're sort of the same generalization of what you had before. So basically, you're taking summations of polynomials applied to the same points. And these polynomials are a basis of all polynomials of degree up to n and d variables. The only difference is before, in 1 variable, that's just n. Now it's sort of much larger number. That's the trouble, okay? And you'd sort of maybe expect or hope that you could do better than that. especially, okay, so there's some lower bound recently, which also, based on dimension makes sense, but you should have, the number of separators should be, at best, the best it could be is n times d. There's no construction in that paper that achieves that. Okay, but we'd like to do that. And sort of the spoiler is that, eventually we will find separators in this talk with m, which is 2nd plus 1. So it's sort of twice what we wanted. And also these separators will actually be, instead of taking polynomials here, they will actually be neural networks. So basically they would solve this other issue, which we talked about, that maybe, the analysis should work with neural networks and not with polynomials. Okay, anyway, so that was the permutation. Let's go back to the special orthogonal example. So there, we also have a similar issue, right? So we're talking about generators. You have this action. The number of generators is more or less n choose d, and they look like this. They're basically the same polynomials we saw in the example in 2D. So there were 4, but again, when the dimension grows, this becomes pretty big. So you can look at all pairwise distances and all norms and all determinants of d by d submatrices. So assuming when d is much smaller than n, this is sort of dominated by this term, which is more or less n choose d. So again, it's a pretty big number. Okay, and you can prove that any SOD function can be approximated by this type of function when n is a fully connected neural network. But again, it seems difficult to believe that anyone would actually implement this because of the dimensionality. Okay. Or I don't know, maybe for d equals 3, which is what usually happens, maybe it's sort of borderline feasible, but it's a challenging. Okay, so that's our situation so far. And then, okay, so the good news is you can do better. So one angle, again, sort of the general angle, like the parallel to Hilbert's theorem, is a much less famous theorem, but also nice, which says that there always exists separating invariants of dimension twice the dimension plus 1. So that's a general result. So generators don't behave very nicely with dimension, but separators do, like the best separators you can find, at least. They're polynomial. And again, like we asked before, you could ask, well, can we actually build them? So then in general, the answer is like yes and no, I guess. So the way the proof essentially works is you take a bunch of, you say, I know that there is some finite set of separators. So let's say the generators. And then you can take these and sort of project them down linearly. And for almost every random projection, for generic random projections, that's going to work. So that will, you will, by construction, it will be invariant. It will also retain separation, even though you reduce the dimension, as long as the dimension of the projection is twice the dimension plus 1. So that's nice. But, in terms of, okay, wait, maybe I'll first also mention. So I think that this is very related to this paper, which also by Cahill and other people who also discussed this whole separation angle, I think the first in sort of the machine learning world, and also used some sort of linear projection to reduce the number of invariants. And you can, I don't know, at least we prove this relatively generally that you can always do this. And maybe, essentially, I guess it was proven before also, but that's not 100% what we want because in terms of complexity, you're still at the end of the day, you have the same, the number of generators is large, the number of separators is small, but the complexity of computing each separator is still large because you have to first compute all the generators and then project down, take some combinations of them. So you could, you could think of cases where that could be helpful, but at the end of the day, it's not all that we want. We'd like to also have low complexity. And so we have a method that does that, at least sort of in some cases. And in particular for these two cases in this table, again, we'll start with here. We'll sort of explain how it works, right? So in SOD, this was our situation. These were our generators. And then we had, okay, and then what we suggest, or what we start from, is we build a continuous family of separating invariants. So you look at basically a parametric function of x1 and xn. You also have the parameters little w and capital W. And basically, it has the following properties. First of all, for every W, little w, capital W pair, this is invariant. And secondly, there are choices which basically gives you back the generators, right? So say if you want to take the norm of the first point, you can take W1 equals 1 and all the other things to be 0, and you can do the same thing for all the other things here. And as a result, I mean, what we really need is you basically, if you can always separate using this sort of infinite family of invariants, just like you can with the finite family. You can now do it with an infinite family, which does sort of may seem like a step backward, but it isn't. So what you can do is basically show that if you randomly choose the parameters of these W's, and the dimension is like before 2ND plus 1, then these things will be invariant and separating. Okay, so it's sort of similar to what we had before. You have 2ND, twice the dimension plus 1. For us, the dimension is n times d, because that's the dimension of the point cloud. You have twice the dimension plus 1 separators, but chosen randomly, but you don't have to compute all the generators first. You can sort of do it in a more efficient way, right? So instead of, previously we had to compute all of these and then maybe do some linear projection down, now we just have to compute something like this, and you do that 2ND plus 1 times, and the complexity of computing each one of these is sort of similar to this. It's again, if n is larger than d, then it's sort of dominated by this matrix product, I think. But so it's nd squared, but it's much better than you had here. Okay, so that's that. And so so what I want to do next is sort of explain how we got to this. I mean, what we use to claim that you can actually just choose the W's randomly and it's going to work, right? So what we saw before, you can rephrase that as saying that if x and y are equivalent, if and only if the difference between h of x and h of y will be 0 for all parameters, right? Because we saw that if x and y are different, then there will be some parameter that separates them. And then, right, so essentially what we want to show is for generic W1 to W2 and D plus 1, the dimension, you have this relationship, right? So basically the same, the set of x and y that you can define by all these infinite constraints, it will be the same as those that you can define by 2ND plus 1 constraints. Okay, so we call this the finite witness theorem. So you can find like a finite number of witnesses that are going to make this work. Okay, so if you want to be sort of even more clean, so we could just, we could call this function h minus h, we just call this f of x w, where this little x encodes capital X and y, and this little w encodes the previous little w and capital W. So we basically just need to prove that if f of x, the set f of x w equals 0 for all parameters w is the same as this set for a finite number of w's, which is twice the dimension plus 1. Okay, so this is, right, the theorem. Okay, so this is essentially, this is like in this paper, the first paper this talk is about, this is essentially what we proved. We used sort of more complicated notation, which now we know maybe we shouldn't have. But basically you prove that if you have some polynomial, then you have f from Rd times Rdw to R, then you get this result, right? For Lebesgue, almost every choice of parameters, which here is, you need capital D plus 1 parameters. You have this equality where the set defined by the infinite number of parameters is the same as the set defined by the finite number. Okay, and again, the translation to what we saw before is, right, if our f is actually a function of 2 parameters and it looks like this h, right, then this d, capital D is basically twice the dimension there x and y live in, and you get 2ND plus 1 in our example, right? So x and y in Rd times n. Okay. Okay. And basically this proof came from, and it was sort of an adaptation of something which you could say essentially uses the same tools. There's a very famous paper on phase retrieval, which shows that phase retrieval is sort of separating with a linear amount sort of we generalize that. Okay. I have something here about the proof. Maybe I think I'll skip it. Okay. Right. So I want to talk more about applications. Oh, sorry. Okay. So right, I forgot my right. So what I was trying to say here, right, is we have basically we now finished explaining the SOD example, and now we want to move on to SN. Now for SN, again, in this first paper, we had sort of polynomial solutions for SN, but now we have better things. So we're going to move on to a sort of generalization of the finite weightless theorem. So in this generalization, we're going to say, basically, the generalization is saying that F doesn't have to necessarily be polynomial. It could also be analytic. And that sort of, we'll see, is sort of very helpful for the type of things we want to prove in the machine learning world. And sort of also, again, we didn't discuss the proof before, and I'm not going to discuss it now, but it's interesting. It's sort of the transition from polynomial to analytic is related to a whole field of moving from real algebraic geometry to sort of more general structures, which include analytic functions and have the same nice properties that polynomials have. And that turns out that it doesn't generalize so nicely, and there's a lot of work on sort of various classes of like sub-analytic sets and all minimal systems, which are so it's a sort of whole field, but again, not going to go into it now. Okay, so the bottom line is this theorem can now work for analytic functions too. And using that, we can go back to the permutation case and look at this basically the same type of neural network we discussed previously. So you have basically what we said, right? For permutation invariant functions, you can, the sort of deep set philosophy would be to apply some neural network to all points and then sum. So here you can do that, and this is actually a very simple neural network with only one layer. I mean, only one layer. Okay, so here it's sort of, so you can write it sort of row-wise. It looks exactly like this. And what we need for the theorem to work is that sigma should be analytic, so that the finite weightless theorem works, and also not polynomial. That's for different reasons. But in any case, the bottom line is you can show that this type of function will be separating. So if you have, if you're in R d times n, you will need, if you have 2n d plus 1, things like this, it's basically like a network of width 2n d plus 1, then this will be separating. Right, okay, so basically the way you prove this, so this is like the H we discussed before. And you show that that for fixed x and y, if they're equal, if and only if, up to permutation, if and only if you have this equality, or in other words, you show that the infinite family of w's and b's can separate x from y, which is, you can show basically using the fact that these networks are universal because this activation is not a polynomial. And then the next step is to use the finite weightless theorem to show that you can move from this sort of infinite separation result to a finite separation result. So that's the result. Okay, so again, that sort of proves from the standard n plus d choose d polynomial construction. And it's sort of, so we got to 2n d plus 1. Recently, there's another paper which got this down by one more using a different construction. There are various details about differences. Don't want to talk about it now, but you can read it here.
Sorry, can I ask a question?
Yeah.
Yeah, why is it that this breaks down if it's polynomial, the argument that you had in the previous slide? Why does it break down?
So it's not the here.
Yeah.
Right.
What
So
happens
what
if it's
breaks down is the separation part. I mean, so the fact, what breaks down is that you can't always separate even with an infinite number of parameters if it's a polynomial. Sigma is a polynomial.
Okay.
So the example, I mean, so one simple example of sigma is just, let's say, linear.
Mm-hmm.
You can see that any
Okay.
x, if you have xi and yi, they sum to the same number, you get the same result no matter what w and b you choose.
Yeah,
But that
okay.
works for
Thank
higher
you.
degree polynomials.
I see. Thank you.
Right. Thanks for the question. Okay. One more thing which is useful is that this theorem can be generalized more in that you can take the domain to be, some reasonably a low-dimensional set which has satisfies some weak regularity conditions. We call it a sigma subanalytic set. So it could be, for example, a countable union of semi-algebraic sets. Let's say something like this. Anything defined, basically like a countable union of anything defined by polynomial or analytic constraints. And so the advantage of that is that you can work with the intrinsic dimension of the domain, right? So the number of separators you'd need would be like this, d plus 1, or where d is the dimension of this set X. So that's useful. So for example, one example is, if we go back to this case we talked about before, but right, we have this permutation invariant functions, and let's say instead of rd times n, we're going to look at some set a to the n. So a is some alphabet where these xi's are coming from, which is a lower dimensional. Let's say, I don't know, some line. So then the number of separators you're going to need is 2nk plus 1 instead of 2nd plus 1. So that's nice. In particular, one case that's sort of studied most in the literature is the finite or countable set, because sometimes your alphabet is finite, and then k is 0 and you only need 1. Okay, that's also a result you can maybe get without this analytic, without some of our machinery, but in any case, you get that. So again, this is, I said in the beginning that this is basically known that you get separation with a single function here with m equals 1, but I don't think there was no such result with a neural network. So now we can show it with a neural network, true with analytic function activations. So now it doesn't work for ReLU, but it does work for many other activations, sigmoid, whatever, anything that's smooth, basically. Okay. Yeah, so we're sort of out of time, right? So that's it. I'll run through this. So now I just wanted to talk about a little more things from a bird's eye. So this is something we did like maybe a year ago. I don't know. Anyway, we've been doing several things which are related to this. But also, right, so this is a paper which actually used the finite witness theorem without, which is not ours, but there are various other, so that's nice. So that's called max filters. There are various things you can do with this, permutation weighted frames. You can, so again, you can go back to phase retrieval where basically this came from, but now you can deal with, because we can deal with sort of general sets, you can work with general semi-algebraic priors, which includes various priors people have considered. And also, you can talk about graphs. I'll run through this in a second. So also about graphs and O3 times SN separation. I'll talk about this now. Okay, so right. So basically, there's a right, in high level in the world of graphs, separating graphs is hard. It's not like separating point sets. Generally, there's no known polynomial algorithm to separate two different graphs up to permutations. So there, we don't really want to separate completely. We want to separate up to some equivalence class of graphs. So one famous result sort of in the GNN world is that message passing neural networks they can't separate all graphs. They are as separating as some sort of test for graph isomorphism called 1W-L. But to actually be as strong as 1WL, you need the network just to be expressive enough, essentially just to be, well, never mind. Yeah. And what you can show is that if you take these message passing graph neural networks and you use so some sort of simple architecture like GIN, and you use analytic non-polynomial activations, then you can actually separate like 1WL even with a single neuron per node. Okay, so that's essentially a parallel of what we talked about before, where if the alphabet is finite, okay, we're going to assume this graph is sort of combinatorial and it has a sort of a finite number of features that it can get. Then one dimension is enough for separation. Okay, and this is something you can actually see sort of in practice. If you do a separation example, you look at, okay, here we took 600 graphs from some data set, the TU data set, and you try to see if the message passing is equivalent to 1WL. So if you take analytic activations, you get 0 errors. So you always separate what WL can. And if you take piecewise linear activations, whether it's ReLU or leaky ReLU or hyperbolic hard tang H, so you do get some errors, especially if the dimension is 1. As you increase the feature dimension, eventually the number of errors decreases. So that's something you can see. You can also see something similar. We have similar results also for 2WL test, which is a more sophisticated graph test, and this PPGN network, which can simulate it. And again, it's known that these are essentially equivalent under various assumptions on the way you implement the PPGN architecture, but we can actually show that you can take it with a very small number of features, and as long as activations are analytic, you can separate. And here you see like you have basically 600 graphs, that's the x-axis, and you have here you're looking at the difference between what your network gives for the first graph and the second graph, okay? And this is the norm, so you see that, okay, and again, this is f theta is a network with 1 neuron per node, and you get this type of behavior. So you see that for each one of these 600 neurons, you don't really get, you always get something. You don't get 0 for all the 4 activations, for all of the first 3 activations we tried, the green and blue and yellow, but for ReLU, you don't. Okay, so you do actually have like at least 200 graphs where you can't separate. Okay, this also shows a sort of slight shortcoming of this theorem is that, with 1 neuron, you can separate, but as you maybe could expect, it's, the separation is not super strong. So you see that the differences are rather small, and really you need, I guess, more neurons to actually get a separation, which actually is sort of meaningful in terms of actually being able to do something with it. So, yeah. Okay, this I think I'll also, I don't know. I mean, I guess we're sort of out of time, so I can sort of skip towards the end.
If there are, I think you can continue unless there are questions from the audience right now.
Okay.
No, so please continue.
Okay, so I'll say like, okay, so just like, right. So, okay, so one thing we sort of, again, this is very bird's view, but one thing which we also worked on recently is basically like this case of, okay, well, you see in this example, this is called the n-body problem. You have 4 different nodes in this case, in general n, and you have their positions and their velocities. And you'd like to know, there's some physical forces interacting with them, and you'd like to know, to learn what the function which takes these from t equals 0 to t equals 1 is. This is a sort of, it's interesting because it involves a lot of, so it's also permutation and rotation and translation something. So if you permute and rotate and translate these points, you basically expect to see the same thing happening here, same permutation, rotation. So this is permutation, rotation, translation, equivariant, which we didn't really talk about to this point. And there are also this issue of, you have also positions and also velocities. And we basically, we have a model which can approximate all functions like this using basically the tools we discussed now and also a lot of different tools. So it's related to various papers which sort of did things along the way. So there was a big jump here from only rotations and permutations separately and invariant to rotation, permutation, translations, and positions and velocity, and also equivariant instead of invariant. So all these things. So Villar talks more about using invariance for equivariant universality, and Rose talks about separation of rotation permutations together. So various things. Okay, and this model also actually seems to work pretty well. So for this n-body problem, it is a little bit better than basically all methods that we know of. In terms of the mean squared error, the prediction it makes, it also performs pretty well in some other generation tasks. Yeah, and that's it, I guess. So I guess the bottom line is that, there's this finite witness theorem, which I think, we found it very useful, and I think also I hope other people will find it useful. I think it's for separation type theorems, it's very useful. And we have, we show that this is useful by showing some improvements of classical expression results for multisets and graphs and other things. And yeah, lastly, I'd just like to thank my collaborators. So there were various ones, but mostly there's Stephen Gortler from Harvard and Tal, the postdoc from my team, who's here, and Snil, who's a PhD student. And these are basically the main references in the talk. These two papers, one from Spotlight in NeurIPS and another will appear in the Foundations of Computational Mathematics journal. Thank you.
Thank you very much for the very nice talk. Are there questions from the audience? Go ahead.
Can I ask a question?
Sure.
Okay, I would like to know if the methods you illustrated can be adapted to the case of G not being a group, in the case that G is just a collection of transformation. What is your opinion about this?
So G is not a group, and what do you want to adapt to that?
You haven't a group, so a structure with some properties with respect to the operation you have. Okay.
Yeah.
In the case you have just a collection of transformation, and you wish to have equivariance in the sense that you have a partial operational composition. The composition is not defined for each pair of transformation. And could you adapt the methods you illustrated to this case?
Well, I guess, that's a good question. I think two things come to mind. I'm not sure. One point in terms of the theorems itself. So there's sort of the raw theorem, this finite witness theorem is just related to, an analytic function. It has no, actually initially in the first paper, it was related to group invariants. And then we discovered that really the theorem itself has nothing to do with, it's just a theorem about analytic functions or polynomial function. So in that case, in that sense, you could use this theory, you could use this to, in general, if you want to show that something is separating, you can build some very large continuous family which separates, and then you can just find a finite sample which separates. So, but that's sort of jumping ahead a few steps, I think.
I understand. It is
no, but in terms of like how to define what the analog of equivariant in that case is, I think, don't know. I think if you have a set of transformations and you're fully equivariant, then really you're equivariant to like the group, you will end up being equivariant to the group generated by that set of transformations.
What I'm thinking is just when you rotate a 6 number, you can rotate a little bit, but you cannot rotate too much. Since when you reverse the 6, it is a 9. So you can compose small rotations, but
Right.
not many times. This is the question of my question.
Yeah, I agree. But then I think, I mean, so I think you need something like sort of continuity and not, you don't want to, if you enforce that rotation of a little bit won't make any change, then that means that if you do that again and again and again, eventually you will get the
so
rotation you were worried about.
You need to remove the possibility of composing any pair of element in the group. You have just a partial definition, but I wouldn't like, this is just a question. I understand that it is outside your plan.
Right. Yeah, it's a good question. I agree. Yeah.
Thank you so much.
Yeah.
I have, yes, go ahead. Yongsheng?
No, you first, go ahead.
Okay, so do you have any intuition on like the qualitativity of the separation? So how large does the dimension need to be if you want the graphs to be separated by some distance?
I think the short answer is no. There are some things we know which aren't necessarily positive. So let's say in one of those papers, we actually show that this thing which is separating is never by Lipschitz. Again, sort of in the strict sense. So it's actually, and then there's some sort of, I think we need to think about sort of more empirical by Lipschitz. So really, so there are some pathological cases where it's going to fall, but that also depends on other things. Yeah, but I mean, the short answer is we certainly don't have any good, any positive results which say anything about that. I think that in the slide, in the picture over there, that they mentioned seemed actually wasn't very large. So no, we don't see anything here. Sorry, I was thinking of something else. Okay, so yeah. I mean, I think often it's not that small. In the experiments, it's not very big, but it's sort of theoretically it's infinite in the examples we talked about. And there are other papers about let's say this max filtering thing, and there was sort of the bi-Lipschitzness of that, and various other things. But I think often we don't know as well to sort of quantify how good the bounds are. So there are, it is by Lipschitz if the dimension is such and such. But what exactly the ratio between the upper and lower Lipschitz constant is sort of, there are bounds, but I'm not sure they're very tight. Not sure.
Yes, thank you. And Yongsheng, you also had a question.
Yeah, yeah. I guess my question is a bit similar as well. Like, so you do these random projections and somewhere in the end to. So I was wondering, like, if you want to show like some sort of separation gap kind of thing, can you? I don't know if the ideas of, let's say, like Johnson's and Lindenstrauss kind of thing argument could they work here in this setting?
Maybe.
Yeah, let's suppose that your generators are like, let's say that the generators that you start with are actually they separate by some amount. Then by doing some sort of random projections to a smaller set, maybe they don't lose that much. I don't know.
Yeah, I mean that part I guess would probably work, but I think what I'm less. I mean, I think what is challenging is to find any kind of separators, regardless of the dimension, that actually do a pretty good job in being by Lipschitz. Maybe not impossible. You have to find something that works well, and then you can, maybe project it down and do such stuff. But the first part is, I think, harder. So I don't think we know in general that the generators will work well. There is also these things about bi-Lipschitzness. There are also results that basically the smoothness is not so good for bi-Lipschitzness. It ruins bi-Lipschitzness. So functions like polynomials, which are smooth everywhere, and also, what we discussed here, like analytic activations applied to, so that sort of is the cause of lack of bi-Lipschitzness. So again, this paper from the max filters crowd, like Dustin Mixon, people like that.
Okay. Thanks.
Okay.
Okay, I think that's all questions for today. So thank you again, Nadav, for the talk.
Thank you.
And yeah, see you next time.
Bye bye.